Hi there, my name is Neutralize. I'm going to be doing a presentation on caustic percentage treat. Last time I did a presentation on residence time for a continuous process. And the basis of the calculation was density, which is calculated as mass over volume. You need to know that density is temperature dependent. That is because as you heat a fluid, it expands, and its density also decreases. So how do you then measure the residence time for a batch process? The residence time is given by the time between feeding and training of a batch. So which means simply the time when you start to feed in your reactants to the point when you're training your products. For example, let's say it's a reactor. So edible oil refining, the chemical refining process consists of the following steps. It consists of the steps which are degumming, which is the first step, then neutralization, which is termed refining or alkaline refining. There's also bleaching. Dewaxing is optional, which is done for certain oils like sunflower or cotton, but it's not necessary for soybean or canola, for example. Then the last step is deodorization. So what's degumming? So the crude oil from pressing and from solvent extraction is usually blended and then degummed before being stored for sale or further processing. Why do we do this blending? It's because these oils have different characteristics. Hence, you want to average out those attributes. Degumming removes phosphatides or gums co-extracted with oil, as they tend to separate from the non-degummed oil as sludge during storage. The phosphatide content of crude oil varies, but is usually the order of 1.0 to 1.5%, or measured as phosphorus. It's from 400 to 600 ppm. The main degumming methods in use are: one, it's water degumming. So it's using water to precipitate phosphatides. 2% by weight. You can add 2% by weight of your oil. The amount to add is about 75% of the phosphatide content. Using an acid such as citric or phosphoric acid and water, this is called super degumming or acid water degumming. So we use the acid water degumming to remove those non-hydrated phosphatides. They need to be conditioned so that they can dissolve in water, otherwise they won't. So the reduction of the phosphorus content in the degummed oil to less than 5 ppm or parts per million is the principal goal of the degumming process. So why do you want to remove these gums? They affect also the downstream processing. For example, in bleaching and in deodorization, you tend to heat your oil, and if those gums are not removed, they tend to form, and also they make compounds which are odoriferous, which means the oil will smell bad. Alkali refining. So degumming is optional when oil will be alkali refined, since phospholipids are removed at this stage. Remember, your alkali or your sodium hydroxide, it's a dilute, which means it has water. That part of water will also do the degumming. Refining removes phosphatides, trace metals. These metals like your copper, your iron, color bodies, your carotenoids, which means as you do your degumming, color will tend to improve a bit. And as you do your alkali refining, the color will definitely improve. And also, but the main issue you want to remove is the free fatty acid. So what happens? The free fatty acid component of your oil will be neutralized with your alkali or sodium hydroxide, forming a soap. soap, soap and also water, right? So that soap and the water needs to be separated from your neutralized oil. So selection of sodium hydroxide strength, mixing time, mixing energy, temperature, and the quantity of excess caustic all have an important part in making the alkali refining process operate effectively and efficiently. Selection of the caustic soda solution treatment is determined by the type of crude oil, free fatty acid content, past refining experience with similar oils, and refining equipment available. So, is it a batch process or is it a continuous process? And also, alkali refining is a part science and part art. So, it depends on your experience with a particular type of oil. Then you come with the appropriate, recipes of refining that particular oil. In general, the minimum amount of the weakest strength necessary to achieve the desired endpoint should be used to minimize saponification of the neutral oil and prevent emulsion during separation. So usually the endpoint of alkali refining is usually free fatty acid content, which is usually from 0.02 to 0.05. But usually some companies will accept 8.1% free fatty acid or less as their endpoint. Also a color, for example. Some companies will take a 4 red as reasonable color of the oil. So why do you need the minimum amount? You want to prevent this saponification. Saponification is where your alkali now reacts with the oil instead of free fatty acid and forming soap. So this will increase your oil loss. And also emulsion, it's whereby you cannot separate your soap from your neutral oil. There is an operational limit to lowering caustic strength. If too dilute, the emulsion is difficult to separate. And if you have worked in industry, if you use too low of a dilute alkali, you tend to get problems too when you're training your soap stock. More so when you're using gravitational separation. Usually the best results are obtained with relatively weak caustic solutions for low free fatty acid oils and with stronger concentrations for high free fatty acid oils. So for example, the low free fatty acid oils are your canola and also your soybeans, and the high usually it's your cotton. So in alkali refining, oil is first heated to around 60-65 degrees Celsius to reduce its viscosity, so that when you're adding other ingredients like your acid and your caustic, it mixes properly. And conducted with 0.05 to 0.2% on weight basis, concentrated phosphoric acid, right, depending on calcium or magnesium content, and 0.5% acid in the case of oils that contain an initial phospholipid of 600 ppm and higher. So if your oil has higher phospholipid, then you need 0.5% of phosphoric acid. So you mix it with your acid, then you continue agitating. For example, if it's a batch process, you continue agitating for a certain period of time, and if it's a continuous process, you have a mixer, right? So it will mix, and also it has a retention time. So after that retention time, it is then conducted with a predetermined amount of concentrated aqueous solution of sodium hydroxide, right? Depending on the type of oil, to neutralize the free fatty acid present. also to neutralize any excess phosphoric acid and to precipitate phosphates, water-soluble gums. So this will require about 2 to 3% of your alkali solution. So after you put your acid, agitate for a certain period of time, you add your sodium hydroxide, continue agitating for a certain period of time, say 1 hour, all right. Then after 1 hour, it is then conducted with approximately 2 liters, 2% on a weight basis hot water, either before or after cooling to 25 to 45 degrees Celsius. So if it's a batch process, you add your sodium hydroxide, mix for a certain period of time, then you add your hot water, then you stop the agitation and let your mixture cycle for 1 hour to 3 hours. So during the cycling time, what happens is that your sodium hydroxide will react with the free fatty acid with the extra amount of phosphoric acid there, and also it will precipitate the gums, right? So these ones will cycle to the bottom of your neutralizer if it's a batch process, right? So after that cycling time, you'll then drain that water and the soap. Then you remain with the neutral oil. You'll then remain with the neutral oil. Okay, let's go ahead. So the neutralized oil is then conducted with 15% hot water. So that water has to be 5 to 8 degrees Celsius above the oil temperature to reduce the soap levels to less than 50 ppm and phosphorus to less than 3 ppm for a single water wash. So you're saying after you drain your water and your soap, you need to wash that oil because still it contains a bit of caustic, so you need to wash it out. So you use hot water, at least 90 degrees Celsius, but it has to be at least 5 to 8 degrees Celsius above the oil temperature, which means your oil temperature needs to be hot. But if you're gonna use double water wash, the first water wash, use 10% with 10% of hot water using weight basis of the oil for the first water wash. Same applies for the second. So an additional option is addition of citric 400 to 500 ppm to wash water, which practically ensures zero soap and phosphorus content and will sequester any pro-oxidants metals present. So sometimes you find that even if you do your washing, your soap is very high, it's about say 100 ppm. So it's paramount that you add some acid, then it will have lower soap content. Softened water must be used to avoid the formation of insoluble soaps. Alkali refining reduces free fatty acid to less than 0.05. So that's what you want. Ideally, it should be less than 0.03. So your iron and your copper concentration are reduced to below the detection level. So excuse me. So the wash oil is then dried to below 0.1% moisture, most often in the range of 0.05%, and usually cooled to at least 60 degrees Celsius to prevent deterioration. The oil is now ready for bleaching. Yes, some companies don't even cool. You just after washing, your oil goes to a tank. Then just before you do your bleaching, that's when you vacuum dry your oil to that level. Please note, moisture is required, so we want equal to below 0.1% because it helps in the bleaching process. So what are the conditions of alkali refining? Temperature for a short mix, 90 degrees Celsius and only few seconds. Residence time applies only few seconds. So this is your residence time, which applies to any vessel. Long mix, 40 degrees Celsius and 15 minutes. So for this one, there are proprietary standard operating procedures, which I will not talk about here for my company, which means the way these recipes are done, they differ from company to company. Some companies will heat up to 60, some to 80. Heating of oil is necessary to decrease the crude oil viscosity to aid effective mixing of different chemicals. So a minimum, it's 40 degrees Celsius. So what about mixing or agitation? So you need to mix at these revolutions 30 to 35 is the maximum. Minimum is 8 to 10. So ideally use around 8 RTM revolutions per minute agitation. So now let's talk about different types of oils. So I will talk first of all about sunflower. The phospholipid content of solvent extracted oil is higher than that of hot pressed oils. So we are saying the hot pressed oil is less grams. Cold pressed oils contain hardly any phospholipids. So some companies, they tend to use mostly the cold pressed oils because they're easy to process, and this the one from solvent because it's relatively difficult to process. But the best way to do it is to mix them 50% and 50%, then process them. Most sunflower oil are hydratable and may be removed by water degumming. So you're saying the gums in the sunflower, they're hydratable, so you can just use water degumming. Water equal to the amount of phospholipid content in the oil is mixed with the oil with a mechanical mix. Crude oil contains 0.5 to 1.5 phosphatides, phosphorus 200 to 520 ppm, and 1 to 2% free fatty acid. So the caustic strength which you use for sunflower is between 12 and 14 degrees Baume. These are specs of the water waste oil which is now ready for bleaching. The FFA should be between 0.02 to 0.03. Your soap between 10 to 50 ppm, and your phosphorus content less than 5 ppm. Then you have good quality oil which is ready for the other stages, which is bleaching. What about soybeans refining or soybeans? Different oils need different strengths of caustic. It can be neutralized directly without degumming if gums or lecithin recovery is not desired. Therefore, if you don't have any market for your gums, you can just refine soybeans as they are without the degumming process, which means your first step will start with the alkali refining, or you combine the degumming process with the alkali refining. The total phospholipid content in crude soybean oil ranges from 1.85 to 2.7%. Then FFA is between 0.5 and 1%. Poor quality soybean oils are defined by a higher free fatty acid content of greater than 1%, indicating a higher than normal non-hydratable phosphatides content. So if once your FFA is greater than 1% for soybeans, similar applies to canola, you know that it's not of a good quality. So in batch degumming, salt water at the same percentage as the total phospholipid is added to the oil heated to 70 degrees Celsius and mixed sterile for 30 to 6 minutes, followed by cycling or centrifuging. So if you have to recover your lecithin, then you can do degumming, or you can do acid degumming, whereby you use 0.03 to 0.1% of 75% phosphoric acid. So a well degummed soybean oil should contain less than 50 ppm of phosphorus. So if you calculate the amount of caustic to add based on the equation, which I will show in the next presentation, you need to add the excess, which means you don't add exactly what is required according to the neutralization reaction, of which I will discuss that on the next presentation. But we add more, so that percentage excess is 0.1 to 0.12 for crude decoupled oil, or 0.1 to 0.15 for crude oil. The caustic strength for soybeans is between 14 and 18 ppm. So it's either you do the water degumming and you add 2% water, 2% of the oil water, using weight basis. This leaves 100 to 200 ppm of phosphorus, or 0.25 to 0.5 phosphatides in the oil. Or else you can do the acid water degumming, whereby you also remove the non-hydrated phosphatides. You can also use 0.1 to 0.5% of 50% solution of citric acid. But mostly in industry, just use phosphoric acid. You then add 2% water after. So about 1 to 3 hours of resistance time is then given in the continuous state tank reactor, or the neutralize. So what happens if sometimes you can combine the on acid and water degumming. So which means you first put in acid, agitate for some time, then stop agitation, add hot water, and let your solution set for some time. Then you can drain the gums beneath and leave your oil on top when doing batch processing. So residual phosphatase concentration is between 5 and 50 ppm of phosphorus. So for canola, this is for alkali refining, you use 12%, which is 17 to 18 ppm. So crude oil is brought to about 60 to 70 degrees Celsius and conducted with about 0.05 to 0.1% of concentrated phosphoric acid, or 0.1 to 0.5% of 50% solution of citric acid, with very intensive mixing. It is then conducted with approximately 12% concentrated aqueous solution of sodium hydroxide to neutralize the free fatty acids present, and also to neutralize any excess phosphoric acid and to precipitate phosphatides. So this requires about 2 to 3% of the solution, which is the alkali solution. So here we are combining the degumming and alkali refining, which means you first condition your oil by adding an acid, agitate for a certain period of time, then add your alkali solution, agitate for a certain period of time, then add hot water and let the mixture cycle for some time. Then you can separate your gums. Your gums, you can separate also the water. You can also remove your soap, because those gums will be part of the soap now. Waste products. So what other waste products do we get besides soap? So we get our wash water. So this goes to the treatment plant. You want your water to be neutral to reduce the biological oxygen demand, to reduce your chemical oxygen demand before you can let it go to drainage, to the municipal drainage. So there's also the deodorizer distillate. This is used to recover sterols and tocopherols. These are natural vitamin E by the pharmaceutical companies. So you can sell it to pharmaceutical companies. But this will come later on when you're doing the deodorization of oils. Then there's soap. So it's added to meal or can be acidulated and used as a feed fat. So I'll talk about this acidulation later on. So the soap stock consists of water, free fatty acids, neutral oil, phospholipids, unsaponifiable matter, proteins, and other substances. Soap stocks are quite alkaline, so their pH ranges from 10 to 11. So they are generated at the rate of about 6% of the volume of the crude soybean oil refined, which is more or less similar to canola, but cotton tends to give more soap stock. I'll say almost double that. So the way you calculate how much of volume or how much mass of the alkaline solution, we use a formula known as percentage treat calculation. So the caustic strength of 17 to 18 degrees Bome are usually prescribed for oils other than palm or palm kernel and coconut. So which means if you're gonna and also other than obviously cotton, but for soybean, right? For canola, for example, we are safe with 17 to 18 degrees Bome. So, but these ones, the palm kernel and coconut, will require a weaker caustic of about 12 degrees Bome to optimize centrifugal separation, reduce saponification of neutral oil, and minimize emulsions. So it requires less. It requires more dilute alkaline solution. Most oils are refined with 0.1 to 0.13 excess. So which means but there are important exceptions. For example, is the oil decammed or not? If it's decammed, obviously we use less. If it's not decammed, we need more excess. So remember, we said this excess caustic. You first calculate the theoretical amount you require neutralization reaction, and we'll discuss about it in the next presentation. Then you add this excess. Lauric and palm oils require a minimal excess of about 0.02%. So if you are going to neutralize, for example, palm oil, your excess will be much less because they are refined for free fatty acid reduction purposes only, not color reduction. So this is the percentage treat formula. So percentage treat, the treat is equal to percent free fatty acid multiplied by 0.142 plus percentage excess all over percentage sodium hydroxide, which is the strength of your alkali solution, plus percentage acid addition times 0.186 or percent acid multiplied by 100. So in the next presentation, I will do one example using this formula. Then you know how you would calculate the percentage treat, or how much amount in terms of percentage of the alkaline solution to add. So what's the refining efficiency of the neutralization reagents? So percentage efficiency equals to product output weight percent over crude oil import times 100. So which means, for example, for a batch process, I will fill in my neutralizer, or some prefer to call it a continuous state tank reactor, Then after that, I'll know how much oil is there in terms of mass, right? Then I'll do my neutralization, everything. After draining my soap stock, after doing water washes, then also I'll know how much oil I have there, right, in terms of weight. So I'll divide that so I'll take the product output over the initial crude oil input, then multiply that by 100. I also do example, and we do this by taking dips, which means I measure the emptiness on top. So by knowing the emptiness, you can convert that using simple calculations to get how much oil in terms of weight you have in a neutralizer. And again, thank you for watching. And if you have any concerns, queries, questions, additions, subtractions, contact me on my email address, stewartsponded@gmail.com. Do not miss out the next lecture because it won't be theoretical, but it will be calculations. These calculations can be very, very hard if you don't work in the oil industry, or if you have never got the chance to actually calculate the stuff which is required and implement it. So I'll tell you, do not miss the next presentation. Until then, I'll see you guys. Do not forget to like, subscribe, and keep watching my YouTube channel so that it goes. That's all I'm asking for you guys. Peace out.